Here we want to evaluate the product of these four matrices, but before I can do that, what I'm going to have to do is determine what each one of the matrices actually is by finding its inverse. If I look at the first one, notice it's a permutation matrix, and the inverse of a permutation matrix is a permutation matrix, which is just the transpose of the original. So the inverse is going to have a column, first column 0, 0, 1. Second column will be 1, 0, 0, and last column will be 0, 1, 0. This second matrix here is a Gauss transform, and the inverse of a Gauss transform is another Gauss transform where the entries that are the transforms are the negation of the original, because it undoes what this Gauss transform does. So this will be a -1, this will be a +2, and that will be the inverse. This is the diagonal, and the inverse of a diagonal is another diagonal where the entries along the diagonal are just the multiplicative reciprocals of the original diagonal entries. So the diagonal here would be -1, +1, +2. And again, it's a diagonal matrix. Now the last matrix here is a little bit unusual. There are -1s in each one of the entries. But notice from the last, or one of the last problems we did, if we had -1 times A and we were trying to find the inverse of it, that should be 1 over -1 times A inverse. But 1 over -1 is -1. So this should be -1 times the inverse of what actually is another permutation matrix. So it's going to have as its entries the first column 0, 0, 1, second column 1, 0, 0, and last column 0, 1, 0, since it will be the transpose of this permutation matrix once I have factored out a -1 from every one of the entries. In other words, I write this as a scalar times a permutation matrix. Now, this scalar here can actually be brought out of the entire multiplication. So what we have here is -1 times 1, 0, 0, -1, 1, 0, 2, 0, 1, and then times -1, 0, 0, 0, 1, 0, 0, 0, 2, times 0, 1, 0, 0, 0, 1, 1, 0, 0. Now, I think I skipped something though, didn't I? I forgot the first matrix here, 0, 1, 0, 0, 0, 1, 1, 0, 0. And then I could multiply everything by -1. So let's do this multiplication first. And I end up with -1 times 0, 1, 0, 0, 0, 1, 1, 0, 0, times, let's see, I have this Gauss transform times this diagonal. Now what does multiplication by a diagonal matrix on the right do? If we partitioned it by columns, what we'll notice is that each of the columns of our original matrix get multiplied by the value along the diagonal here. So this multiplication result will be the first column needs to be multiplied by -1, which would be -1, 1, -2. And the second column would be multiplied by 1, giving us a 0, 1, 0. And then the last column should be multiplied by 2, giving us a 0, 0, 2. Now, what happens when we multiply a permutation matrix times another on the left or the right? Well, notice that in this particular case, it doesn't matter the order. What we can do is multiply first on the right by this permutation matrix, which is going to switch the columns of our matrix. And so this is going to be -1 times the matrix 0, 1, 0, 0, 0, 1, 1, 0, 0 times switching the columns. Now we'll have the third column first, which would be a 0, 0, 2. And then we're going to have the first column, which would be -1, 1, -2. And then we're going to have the second column, which would be 0, 1, 0. Then this permutation matrix switches the rows. We'll have the second row first, 0, 1, 1. The third row next, 2, -2, 0. And then the last row will be the first, 0, -1, 0. When we multiply by -1, we end up with 0, -1, -1, -2, 2, 0, 0, 1, 0 as our resulting product.